All right, guys, Mr. Antonucci here, and in this video, we're going to prove the formula that we learned in geometry for the volume of a sphere using calculus. So what we're going to do is we're going to start with a picture of the sphere here, and we're going to superimpose it on a standard X and Y coordinate plane, and the sphere is going to be centered at the origin. The volume of the sphere is volume equals 4/3 pi, and we're going to use capital R squared here, where R, capital R represents the radius of the sphere. So it goes from positive R to negative R on the x-axis, and it also goes to positive R to negative R on the y-axis. Now, what we want to do is vertically slice a section of that sphere and pull it out, and it's going to be perpendicular to the x-axis, and you can see it here in green. Okay, if we flatten that slice out, it would be a circle, and the radius of that circle actually corresponds to the y value because we have this distance from the x-axis to where that slice is on the sphere. So at any given x coordinate, the radius of that cross section, that circular cross section, is given by the y value. Now, if we look at the sphere as a circle, the formula for the circle that encompasses the sphere is x squared plus y squared equals r squared. So that implies that y equals the square root of r squared minus x squared. Okay, if we just solve that for y. The reason that's important is because that gives us a way to determine the value of y, which is the radius of our slice. Because the area of that slice is pi r squared, and the radius of that slice is the y value, and that y value in terms of x is square root capital R squared minus x squared. So it'd be pi times square root r squared minus x squared, quantity squared, which simplifies to pi times capital R squared minus x squared. Now, since x is a continuous function from negative r to r, we can get the volume by integrating the area function from negative r to r. Okay? Now, what goes in here is pi times r squared minus x squared dx. I'm going to do two things right here. Since this sphere is symmetric with respect to the y-axis, I can double the integral and integrate from 0 to r. That's very helpful when we go to evaluate it after we anti-differentiate. Also, I'm going to factor the pi out since the pi is a constant multiplying everything inside. Then you have capital R squared minus x squared dx. Also, keep in mind that capital R represents a constant and we're integrating with respect to the variable x. So this would become capital R squared times x, not 1/3 r squared, not 1/3 r cubed. However, the x squared becomes 1/3 x cubed. And we're going to evaluate that from 0 to r. So you have 2 pi times the function evaluated at r, which would be r squared times r minus 1/3 times r cubed minus the function evaluated at 0, which is going to just be 0. Now, you have 2 pi times, this would be r cubed minus r cubed over 3. Now you could think of this as 3r over 3. So when you subtract, you'd have 2 pi times 2r cubed over 3. Multiplying by the 2 gives us 4/3 pi r cubed, which is the volume of a sphere. Just proved it using calculus. I think that's pretty cool.